first of all, we need to convert the second order to state space. So in order to create state space representation, we need to create a state vector. So let's name this state vector as y, and then this y should have displacement and velocity in it. So again, if you recall what we learned during the ODE 45 lecture, the order of these state variables doesn't matter. So you can put velocity first and then position. Here I just define the y in this way. And then in order to find these state space representation, we know that we need to create a function or create an equation in this format. All right. So what is y dot? Y dot is just time derivative for each entity. So position becomes velocity. That is your y dot. And then velocity becomes acceleration. And then the next step is we need to use state variables to describe your y dot. Luckily, your x dot is directly one state variable. So we know that if we put it as x and x dot, so it's just 0 and 1, right? Because that means x dot equals to 0 times x plus 1 times x dot. That's correct. So what is x double dot? For x double dot, you have to go back to the original ODE. X double dot equals to minus omega n squared x plus f naught cosine omega t. All right, so that means you can describe your x double dot by using x and a constant. So this x is one of your state variable. So you have to copy the coefficient for the x, put it in the first column, and then there's no x dot in it, so it's just 0. And then all these constant, or I shouldn't say constant, all the terms that has nothing to do with your state variable, they belongs to the b times u part. So in this case, that's f naught cosine omega t. So this b times u has all the terms without state variables. All right. Then the first equation, because just x dot equals to x dot, so no terms without state variables, so just 0. So up to this point, we find out our A matrix is 0, 1 minus omega squared, 0. And then you can plug in what we have here. That's 0, 1 minus 4 and 0. Right. So for the b times u part, we have 0 and f naught. What is f naught? F naught is 1. Cosine omega is also 1, so it's just cosine t. And then we can apply the Laplace transform method we just learned. So we know that your solution in S domain can be written as Si minus A invert times BUS plus X naught, right? Yeah, it's just BUS times X naught. So then you can write these out. What is SI? Your SI is just S times the identity matrix. So you only have S on the in the diagonal terms, but all the other off-diagonal terms are 0. That underlined part is S times I. And then minus A is 0, 1, minus 4, 0. So this entire thing, we need to invert it. And then the second part, we have B and U. As I said, in this class, you can treat B and U as a whole. So your BU is this thing. In order to convert the time domain function to Laplace or S domain, you just need to do Laplace transform for each entity. So it's 0, and then your cosine becomes S squared plus 1 S. So that's the Laplace transform for cosine. 0 stays at 0. So what you do is you just copy and paste this BUS, that is 0 S over S squared plus 1. And then you need to type in your initial conditions. Your initial condition, remember, then you need to go back and check the order of your Y. So you have displacement first and then velocity. So that's why you need to put initial position first, which is 0. Your initial velocity is 1. All right. Then we have everything. So what you need to do is just merge all these terms. When you do these summation or subtraction, you need to find the difference for each entity. So S minus 0 is S, 0 minus 1 is minus 1, 0 minus minus 4, that's positive 4, and then S, you have to invert it. And then the column vector here is 0 and 1 plus S over S squared plus 1. So what this X is, let me check it out. S minus 1 or S All right, I just did these in MATLAB, and then you can find it out that it is S over S squared plus 1 divided by S squared plus 4. And then the second term is S squared plus 1 plus S divided by S squared plus 4. So as you can see here, your solution is no longer a scalar. Your solution is also a matrix. In this case, it's 2 by 1. Then you can do Laplace transform, or I Laplace transform, or inverse Laplace, I Laplace for XS. And then you can get your time domain solution, XT. As you can imagine, you're going to have X1T and X2T, right? Because your XS is 2 by 1. So that means when you do I Laplace, your time domain function, XT, would also be in, actually, I should say that's Y. Otherwise, it got confused. So this is your Y in time domain. This is a Y1T. This is a Y2T. So you actually have two solutions. And then let's recall your Y is position and velocity. So that means your position is just Y1T, and then your velocity is Y2T. So for this method, you're not only getting displacement, you're also solving the velocity. All right, so that's how we apply these state space representation and then use Laplace transform to solve a first order ODE. So then your question might be why we have to do this state space thing, because as we learned in previous lectures, it seems that this method also works fine. So the state space representation is greatly helpful, especially when you have more than one coordinates in your system. So let's look at the example number 2. Before moving on, so any questions about these calculations? All right, so if no questions, then example number 2. So here, last time when we have two mass lumped together, we know that we can write it as M matrix times x1 double dot, x2 double dot. Let's name these as X matrix double dot times some C matrix X single dot plus some K matrix some X equal to some force matrix. In this case, we have no force term, it's just free vibration. We have no damping, so you can ignore this one as well. Then we just need to find out your M and K. All right? So what is M? So last time I taught you a very tricky way to do this. So it has to be diagonal. You just lay out all your mass on the diagonal terms, and then the off diagonal will be 0. And then for the K, what you do is you determine the K through the coupling. So this term means all the springs connected to the mass 1. So you have two springs connected to the mass, is K1 plus K2. This term means you need to find all the springs connected to X2. So it's only K2. And these off-diagonal terms, they describe the coupling. So you need to find out what springs is between the two coordinates. So it's only K2. But also remember, the off-diagonal terms should be negative. So you have to put a minus sign in front. So that's how you find an MK really easily. All right. So the next step is we need to solve these in state space. To solve these in state space, you need to define a state variable first. Let's define it as x1, x2, x1 dot, and x2 dot. All right. Again, the order of these variables, they are just random. The good way to put these in this format is actually more convenient in calculation. So that's why we can write out your y dot. We want to describe y dot using y. Your y is x1, x2, x2, sorry, x1 dot and x2 dot. Because this is a 4x1 matrix, we're expecting a 4x4 A matrix. One, two, three, four. All right. So the y dot from top to bottom is x1 dot, x2 dot, x1 double dot, x2 double dot. So x1 dot luckily is one of the state variable. It's the third state variable. So that means your third column should be 1. All the others should be 0. Your x2 dot is the last state variable. So that's why this is 1 and all the others are 0. And then you have x1 double dot. So that's where you need to do some tricky stuff. Then you have to go back to your original ODE. So your original ODE, we write it in x double dot plus. Okay, we write it in a matrix format. So in order to do this, we have to express it out and then convert it to equations. So that means the first equation is M1 x1 double dot plus k1 plus k2 x1 minus k2 x2 equal to 0. Your m2 x2 double dot plus k2 x2 minus k2 x1 equal to 0. So from these equations, you can describe your x1 double dot in terms of your state variable. It's just k2 x2 minus k1 plus k2 x1 divided by m1. And then you just copy and paste all these coefficients back into a matrix. So your coefficients for x1 is minus k1 plus k2 divided by m1. And then the second one is positive k2 m1. And then all the other terms just 0 because we have no damping. So similarly, you can fill out the last row. The last row is x2 double dot equals to k2 x1 minus k2 x2 divided by m2. And then you just copy and paste k2 m2 minus k2 m2 0 0. So in this case, we have no initial. We do have initial condition, but we have no input or external excitation. So that means the v times u term, that's all 0. So you can ignore it. So that big 4x4 matrix, that's our A. And then you can use the Laplace transform method I just told you. But before moving on, I'm going to emphasize why defining y in these formats, in this order, is more appropriate. So you actually, if you understand these matrix formats, you don't even need to write it out into linear equations anymore. Let's treat your y into two small vectors. All right? So that's your y. You can actually write it as two column vectors, right? Remember that your x is x1 over x2. So that means you can actually collect all these terms into two groups and then form a group of matrix, a group of a state vector. So then what is your y dot? Your y dot is just x dot over x double dot. And then you can write it as large space. So your y is x over x dot. So in this case, we're not writing y as 4x1. It's actually 2x1, 2x1. And then within each entity is actually 2x1 column vector. So overall, it's still 4x1, but then we cut it into two pieces only. So in here, your A matrix will still be 4x4, but then we cut it into 4 sections instead of into 16 sections. So for each section, we're looking for something that is 2x2. Then let's fill in. So the first equation is x dot equals to x dot. We can write it as x2 dot equals to the identity matrix times x dot. So that means your x dot is 0 matrix times the identity matrix, which is 1, 1, 0, 0. And then the second equation is x double dot equals to, then you need to go back to this matrix format. And then you would have M invert times K matrix times X. There's a negative sign in front. All right, so that's your x double dot. You can see that, okay, so that means the first entity is a 2 by 2 matrix. You can write it as minus m invert, okay? And then it has nothing to do with velocity. So the second term is also all 0. So in this way, you don't have to write your original equations out. You directly use matrix operation. All right, so once you have all of this, then we can solve these easily following Laplace transform method. I can teach you how to do these in MATLAB. So the example for these is in lecture 17, underline 2. You can check these live script later. But during class, I can show you what to do. Screen. All right, so first of all, oops, that's too big. First of all, we need to define a variable that stands for the s. So we just define an s variable, and then we already know that the mass matrix M is a diagonal matrix. The first one is M1 is 9, second one is mass is 1. So if you run it, you're going to see we create a diagonal matrix, and then we just need to type in the diagonal terms. And then the K matrix is K1 plus K2, that's 27, minus K2, that's minus 3, and minus 3 and 3. We also need to define the initial positions. So initial positions is 1 and 0, and then initial velocity is 0, 0. All right. So then we need to create our A matrix. If you go back to the lecture notes I just gave you, so your A matrix, we can divide it into actually 4 parts. The first one is a 2 by 2 zero matrix. The second part is a identity matrix of 2-dimensional. And then this one is minus M invert times K. And then the last one is zeros 2 by 2. Let's calculate it. Oops. Yep, as you can see here, that's what you have. And then if you don't want to do, so you can compare this matrix format with the first expression we directly got from row by row. You can see we get the same A matrix. So then we need to find the XS. Remember the XS is S times I minus A invert times X naught, right? So actually in this case is Y naught. We're not doing X. We're calculating the state variable Y. So YS equals to this. And then your Y naught, remember that we organize your initial condition we organize the state variable in a certain way. So we have our position first and then velocity. So that's your Y naught. And then this I matrix, as I said, is identity matrix in order to match the dimensions. So your A is 4 by 4. So these identity matrix should be 4-dimensional as like 4 by 4 as well. So right now you have everything. Let's calculate it. So that's your Laplace, that's all your solutions in S domain. And then in order to find solutions in time domain, So you have yt is just I Laplace, inverse Laplace transform of these S equation. All right, so then you have 4 solutions. These 4 solutions corresponding to your 4 state variables. Remember how we define it. So this is x1, this is x2, and then this is x1 dot. The last one is x2 dot. So in this method, we're getting 2 displacement, 2 velocity. So just make sure you understand which entity is which. All right. So any questions about this? That's how we solve linear systems using state space representation. All right. So any thoughts? All right. Am I still online, or because I didn't get any response?
Yep, still here. Just
Okay, great.
yeah, don't worry. Yeah, this is just gonna be looking over the notes a little bit.
All right.
It's pretty straightforward. So
Yeah. So if you check my note and then just follow this step, I think basically my note is like a flow chart, and then if you compare my handwritten part with my code, I think it's pretty straightforward. So this is the state space representation. So if you work in electric engineering, if you work in ECE, working control, most of the time, I would say 99% of the chance you're going to use this method to solve the ODEs. But for mechanical engineers, we're actually more interested in the second method, which is called eigenvalues and eigenvectors. So the idea is, the challenge right now is, let me put up a new page. So we already done, so in previous lectures, we already know how to solve these equations, right? We can easily find the solution for that, for these, when your x is just a scalar. The problem for our for a multi-degree of freedom system is, if you look at the equation here, in your equation 1, you have both x1 and x2 in it. In equation 2, you have x2 and x1 in it. So that means all the equations, they are just coupled together. So if you are able to get 2 equations like this, some constant and x2 dt d plus fx2 equal to c2. So if you're able to decouple your multi-degree of freedom ODE into these separated equations, then what you need to do is you just go back to our to the part 2 of this lecture, and then you can find the solution very easily. So that's the idea for the second one. So the second method, how can we decouple all your ODEs? So we have to recall a very important idea you might have learned in your linear algebra class. It's called matrix diagonalization. Diagonalization. So when you have a matrix A, we will be able to write your A as, let's say your A is an n by n matrix. Then we're able to decompose your A into 3 matrices. So this P is also n by n, lambda is n by n, P is n by n. So what is P and what is lambda? So lambda is a diagonal matrix, lambda 1, lambda 2, all the way to lambda n. So all the off-diagonal terms, diagonal. So that's your lambda matrix. So if your lambda is at diagonal, so then these P matrix, we have U1, U2, U3, all the way to UN. So these U, they are column vectors. So your U, this is n by n. Your UI vector is a column vector, is n by 1 column vector. Okay. Just cannot spare today. Column vector. Okay. All right. So that's a property of matrix diagonalization. So what we do is we convert a matrix A into a diagonal matrix lambda. The way we do it is we just multiply A by a so-called matrix P. So how can we find your lambda and how can we find your P? So your lambda 1, lambda 2, all the way to lambda L, and we call them eigenvalues of matrix A. And then similarly, your U1, U2, all the way to UN, these are column vectors. We call them eigenvectors of A. So lambda 1 and U1, they have 1-to-1 correspondence. That means for a given eigenvalue, you find the corresponding eigenvector. So that means once your lambda 1, lambda 2, lambda n is organized in this lambda matrix, you cannot switch the order of your U's. That means you have to put U1, U2, they should be coupled in the right order. All right. So later you're going to see that we also call this P matrix coordinate transformation. Basically, we're transforming from one coordinate system to another coordinate. So we're going to talk about this later. The idea here is by using these, we can easily decouple our system. Let's look at what we have. Oh, perhaps I need to give you a refresh of mind how to find lambda and P. So in order to find your lambdas, what you need to do is you need to solve this equation, lambda I minus A, determinant equal to 0. Again, your I is identity matrix. Then you're able to find n solutions. All right, so that's how you find your eigenvalues. So in order to find your eigenvectors, you just plug in lambda I minus A, that's a matrix, times U equal to 0 vector. All right, you just plug in your lambda, for example, in order to find U1, you just need to solve lambda 1 I minus a u1 equal to this. You just need to solve this equation. Similarly, in order to find u2, you just need to plug lambda 2 back in and then find your u2. So 10 years ago, when I take this class, we were encouraged to solve these by hand. But luckily, because of MATLAB, you don't have to do this by hand anymore. In MATLAB, you just use the eigenfunction. The first input of this eigenfunction is a p. The first output is p. The second output is the lambda matrix. This is a lambda matrix. This is a p matrix. All right. So you just put eigen A in it. It directly gives you the p and lambda. So you don't have. So this is just something you need to know, but that might help you to understand the later mode analysis and mode summation method. But for now, you just need to know how to use eigenfunction in MATLAB. All right. So let's go back to these diagonal matrix to see what we can do with it. So let's focus on these first order equations. What we can do is you leave your x there. We know that for the A matrix, we can write it as P times lambda times P invert times X times BU. There's a time dependent input, right? From here, from the first equation to the second one, we didn't do anything specific. That means anything special. We just replace the A by P lambda and P invert. I should put the invert in outside. All right. Then we just multiply P invert on both sides. Then you have P invert X dot equals to P invert P lambda P invert X plus P invert BUT. We just multiply both sides by P invert. As you can see that P invert times P, that becomes identity matrix. You can cancel these out. And eventually what we got is P invert X dot. I'm gonna remove out the bracket just to speed it up. And then you have lambda P invert X plus P invert BUT. So then we do something even trickier. So we assume a new state variable, y. Your y is P minus X dot. Because we know that your P is a constant matrix. So it has nothing to do with time. It's just constant coefficients. So that means P inverse X. So that means when you do time derivatives, you can leave the P invert. You can treat it as a constant. You just need to do time derivative for the X only. So by replacing these, by replacing X by Y, you have Y dot equals to lambda Y plus P invert BUT. As you remember that your BUT, let's say your X is n by n, your BUT will be n by 1, and then the P invert is n by n, and then this is n by n, and also lambda is diagonal. So let's first forget about the last term. Let's just focus on the first part. We will have y dot equals to lambda y. Let's write it out. We have y1 as named as y1 dot, y2 dot, all the way to yn dot equals to lambda 1, lambda 2, all the way to lambda n, y1, y2, and yn. Even though we write these equations in matrix format, but there is a very special property of this, which is you can actually write it out into n equations. These equations are y1 dot equals to lambda 1, y1, y2 dot equals to lambda 2, y2, all the way to yn dot equals to lambda n, yn. You can see a very special property of these equations. They're decoupled, right? Your first equation is only about y1, the second one is only about y2, and keep going. So then you can use whatever we learned previously, as I said, for the scale for the first degree of freedom systems. You can just find your y1 t, you can find your y2 t, you solve them separately, yn t, and then you plug them back in to your y matrix. Your y will be y1t, y2t, all the way to ynt, right? So up to this point, we ignore the additional input term. So if you do want to keep your input term there, let's say p minus but is just k1t, k2t, eventually just an n by 1 time dependent function. Then nothing special. You just need to add these input terms in the end. In order to solve these free vibrations, you just need to solve forced vibration, right? The method is same. We still get the same effect. All your equations, they are decoupled. Eventually, you can find your y solution. But this solution is in y domain. Remember that your y is coupled with your x. How can we find x from y? Your x is just p times y, right? If you multiply both sides by p on the left, then your x is just p times y. So once you have this y solution, in order to get the solution you want, in order to find x, you just need to times your y solution by p. Make sense? So the concept for this is, I'm going to cover this in next lecture, but hopefully you get the basic idea for this. Yes, I don't think I have a time to cover one example, but let me explain the idea again. So the idea is all the original equation, they were defined in X domain. I would say in X domain. So that's everything we want to solve. All the coordinates were defined in X domain, but it's really hard to solve those equations in X domain directly. So what we do is we find the intermediate domain, which is Y domain. So in this Y domain, we have a lot of nice properties. The most important one is in Y domain, all your coordinates, they're decoupled. So you won't have x1, x2, x3 in one equation. You will only have one coordinate in one equation. So then we can easily find the solution in Y domain. Once we find the solution in Y domain, we just dump it back to X domain. So the coupling between these two domains is through the P matrix or P invert. So that's why we call this P as coordinate transformation matrix. We just convert the X coordinate to Y coordinate. So the other way to look at this is you can actually convert a complicated question into a simple question just by viewing it in a different way. So I remember my previous professor, like he gave us an example. For example, how can you quickly draw a water bottle or a cup? So if you want to draw a water cup, like a teacup or coffee mug, that's the best I can do over here, right? Actually, I ignore a lot of details. It's really hard to draw it, but you can actually find some certain angles, make your drawings really easy. For example, in this case, if you look at it from the top view, you just need to draw two circles and a square for the handle, right? So these drawings are actually much easier than creating a 3D drawing for these coffee mug. So that's the concept for this eigenvector and eigenvalue problem. So let's say all these equations in X domain is this 3D coffee mug. Well, it's really hard to draw. It takes you so much time. But then if you change an angle, if you look at your equation in Y domain and then solve it, and then you can easily convert it to X domain. So that's the concept. I can quickly give you an example, perhaps since I already have the equation, the matrix in MATLAB, I can try it out. All right, so let's use this matrix. Let's put a K, X naught. All right, so we have this A matrix here. That's for which example? I think that's for example number 2. So what we need to do is we need to diagonalize this. So as I said, the first output is P, the second output is lambda, and then you're just using eigen A. All right, so then we need to find y dot equals to lambda times y, right? We just find the all these equations in Y domain. How we do that? So eventually we need to find the solution. So in this case, we have no force, so it's all due to initial. I think that confuses things a little bit. I cannot use y because y is already taken. So let me use z. Let's say the z domain is our y domain. So let's say z dot equal to lambda times z. Because no force is all initial, it's all free vibration due to initial condition. So we need to find the initial condition in z domain. How can we find that? So the initial condition, I think it just complicates things. Let me still use x and y so don't confuse you. So the x is, So that's your initial condition in X. And then we don't have that. So let's say that's Y dot equals to Y. And remember that, so we need to do everything in Y domain. And then we only know initial condition in X domain. So we need to convert our initial conditions to Y domain as well. So the coupling between Y and X is through the P matrix, right? So Y naught equals to P invert times X naught. So from X to Y, you need to multiply everything by P invert. From Y to X, you do the opposite. So once you have this, then you have a bunch of equations, which means Y1 equals to lambda 1 Y under these initial conditions. So it's just exponential decaying. So if you remember your math 333, so that means your time domain solution in Y is just, what's the best way to write it? So it's just Y naught multiply exponential term lambda times t. And then I need to define the symbolic t. Oops, cannot use condense. So what we need to do is we need to convert this lambda into a column vector. I just forgot what's the command for that. Anyway, I can teach you these. I can show you these like after class. I just forgot the command, and I think the time is running up. Oops. Yeah, we can go over an example next class. I think it's a little bit rushed right now, especially I confused you about the X, Y, and Z coordinate. I think next time I'm gonna draw you a flow chart. You're gonna see these you're gonna see the big picture much better. Yep. All right. Yeah, nice talk to you. It's been a crazy week. Yeah. Are you keeping an eye on the election results? Man, it's crazy. All right, so hopefully everything can work out, including the big thing and then the small class. All right, see you next Monday.
Thanks.
Yep, bye.